Welcome back. I am Dr. A.G. Srinivasan, Functional Analysis FAV006. Let us continue with examples of metric space. Let X be set of all bounded sequences and denote X is equal to AJ or A1, A2, A3, etc. and Y is equal to BJ, J is equal to 1, 2, 3. Define D of xy is equal to supremum of modulus aj minus bj, where j belongs to n set of all natural numbers 1, 2, 3, etc. Then D is a metric. It follows easily using the fact the supremum behaves like maximum. Therefore, it is a fixed modulus aj minus bj, and modulus satisfies the non-negativity property, the symmetric property, and even the triangle inequality automatically, though the supremum may not belong to the set. So proving it's a metric space is very easy. So this is a metric, and this metric space is denoted by L infinity. It's called L infinity space. Note that L infinity is a sequence space because each element of X is a sequence. Let's take the second example for the day, the function space CAB, where CAB is set of all functions f from a to b to r, such that f is single valued and continuous function. Let x and t, x of t and y of t belong to C of AB and t belongs to AB. Define D of xy is maximum of modulus x of t minus y of t. Again, the maximum is one such element. So modulus x of t minus y of t, we already saw by using basic mathematics. And the modulus x of t minus y of t is certainly a metric. So D is a metric space as readily seen using modulus absolute notion, and the continuity is preserved even in triangle inequalities. Now the next example is as follows. Let X be a non-empty set. Define D of xy is 1 if x not equal to y, is equal to 0 if x is equal to y. Now, if D is a metric, then the metric space XD is called discrete metric space. It's called discrete metric space. The first three conditions of the metric D is very easy, which are non-negative, equal to 0 if x equal to y, or if x equal to y, D of xy is equal to 0 is automatic. It is symmetric because D of xy is same as D of yx, because the output doesn't actually involve directly x and y, because they are not dependent on x and y, though the definition depends on x and y. So these terms are not depends on x and y, but definition depends on x and y. So it is symmetric, it is automatic. The only condition is pending is to prove the triangle inequality. To show triangle inequality, which is D of xy is less than or equal to D of xz plus D of zy. Now when I say less than or equal to, it can be less than or even equal to. Even if inequality comes, it's still a metric space if it satisfies the first three conditions, the non-empty conditions, symmetric conditions, and so on. So let xyz belongs to x. Suppose x not equal to y. I have two cases. Case 1, x not equal to y. If x not equal to y, by definition, D of xy is 1, because x not equal to y, D of xy is 1. So you can easily see that this is 1, which I call it as A. Now if x is equal to z, suppose x is equal to z as a case, first case A, if x is equal to z, because x not equal to y, y is not equal to z. So x is equal to z, by definition of metric, D of xz is 0, I call it as B. Because y not equal to z, by definition of metric, D of yz is 1, I call it as C. So from A, B, and C, you will have D of xy, that is 1, this is 1, this is 1. D of xy is equal to D of xz plus D of zy. Equality holds. So 1 satisfies using ABC. In fact, 1 is the equality. The second case is that in the same way, x not equal to z, and maybe y is equal to z. If x not equal to z, by definition, D of xz is 1. If y is equal to z, D of yz is equal to 0. So I call this D and E respectively. From A, D, and E, you will find again the equality holds, which is D of xy is equal to d of xz plus d of yz. And in case 1, third case, suppose x not equal to z as well as y not equal to z, then d of xz is 1, d of yz is also 1, and I call this f and g respectively. And from a, d of xy is 1, but 1 is less than or equal to 2. Actually, it's less than 2 is required, but 2 can be written as 1 plus 1. I shall replace 1 by d of xz and 1 by d of yz. So d of xy is less than or equal to d of xz plus d of yz. So triangle inequality is satisfied. Now it is strictly less than. Whereas in case 2, x is equal to y. So case 1 says x not equal to y. Case 2 says x is equal to y. If x is equal to y, certainly d of xy is 0 by definitional metric. If x is equal to z, because x is equal to y also becomes z. In that case, d of xz is 0 by definitional metric, d of yz is 0 again by definitional metric. So therefore, d of xy, which is 0 by this, equal to d of xz 0, d of yz is 0, and the equality holds. And the last case, x not equal to z and y not equal to z. You cannot get x is equal to z and y not equal to z. We assume that x is equal to y already in case 2. So x not equal to z and y not equal to z. D of xz is 1 by definition of metric. D of yz equal to 1 by definition of metric. D of xy is 0 by definition of the case 2. So 0 less than or equal to 1 plus 1. In any of these cases, you can easily check the triangle equivalently satisfies. So thus, xd is a metric space, and this metric space is called a discrete metric space. It's called a discrete metric space. Now, before we go to the next example, 7 or maybe 9, I would like to show you one more time what a C of AB is. C of AB is all set of all functions f from a to b to r such that f is single valued as well as continuous functions. So let us now take the next example, number 9. Okay, refer example 6. This is C of AB. Let x equal to C of AB. Define d of x comma y is integral a to b modulus x of t minus y of t dt. Because they are continuous functions, they are Riemann integral in some sense. So we can easily get the value of this which is finite and easily show using modulus property this d is also a metric. This is example 9. Example 8 is x is equal to r. Define d of xy is square root of modulus x minus y. If x minus y are x and y are two real numbers, modulus x minus y is a real number, but it could be negative. Because of modulus, it is positive. So square root is again a real number as well. So easily you can show that using modulus properties, some basic mathematics, that x comma d is a metric space. In the next video, we will see some review on sequences, bounded sequences, convergence, LP space and infinity space under FAV003. See you soon in FAE001. I am Dr. A.G. Srinivasan. Thank you.